Hello everybody, so we continue with chapter 3, sequences and series, and now we're going to look at section 3.6, counting principles. And we will begin with simple counting problems, specifically example 3.31. And it says, each integer from 1 to 9 is written on a paper chip. The paper chips are placed in a box. One chip is chosen, the number is recorded, and the chip is put back in the box. This is then repeated for a second chip. The number on the chips are added. In how many ways can you get a sum of 8? Okay, so how many ways can we get a sum of 8? And it says that the chips are from 1 to 9. So basically we have to think about the different ways we can combine the first chip. So this would be the first chip and then the second chip. So let's say we take out a 1 and then a 7. That's one way to do it. A 2 and a 6. A 3 and a 5. And it says that you put the chip back so you can get 4 and 4, and then 5 and 3, and then 6 and 2, and then 7 and 1. Notice that we don't use 8 or 9 because there's no way you can get a sum of 8 with either 8 or 9. So in conclusion, we can say that there are 1, 2, 3, 4, 5, 6, 7 different ways in which we can get a sum of 8. So now let's take a look at example 3.32. And it says, suppose now that the first chip is chosen and the number is recorded, but the chip is not put back in the box. Then the second chip is drawn. In how many ways can you get the sum of 8? So this is similar to the previous case, but there cannot be a repeating chip. That means that we would have to discard the case of 4 and 4. So let's take a look at it. So if this is the first chip and this is the second, you could draw out a 1 and then a 7, a 2, and then a 6, a 3, and then a 5. But not 4 and 4 because the chip is not put back into the box as it says here. Then we would have 5, 3, 6, 2, and 7, 1. Therefore, there would be 6 different ways in which we could get the sum of 8. So next we have example 3.33, and it says, for making sandwiches, there are 3 kinds of bread and 4 kinds of cheese. Sandwiches can be made with or without pickles. How many different kinds of sandwich can be made? So 3 types of bread times 4 kinds of cheese, and then you also have the option of with or without pickles. So that's 2 different types of sandwiches. So this would simply be 3 times 4 times 2, which is 24 possible sandwiches. So next we have example 3.34, and it says, how many 3-digit even numbers are there? So numbers with 3 digits. Now, if we think about the hundreds, which is going to be the first digit or the starting digit, then we would have 9 possibilities because no number starts with 0. For the second digit, we would have 10 different possibilities because we have 10 digits. But then it says they're even numbers. Therefore, in the third place, we would have 5 possibilities, right? 0, 2, 4, 6, and 8. So this would be 9 times 10 times 5, and this is going to equal 450. So the answer is 450 3-digit even numbers. So now we continue with example 3.35, and it says, a large school issues special coded ID cards that consist of 2 letters followed by 3 numerals. For example, AB 737 is such a code. How many different ID cards can be issued if the letters or numbers can be used more than once? So they can be used more than once. That means that you can have AA111, for instance. Okay, so this is again a very simple problem because all we have to do is a multiplication. There's 26 letters in the English alphabet, So we would say 26 for this spot, and then this times 26 for the next spot. And then we would say there's 10 possibilities for the third spot, times 10 possibilities for the fourth spot, times 10 possibilities for the last spot. This is going to equal 26 times 26 times 10 times 10 times 10, and that's going to be 676,000 different ways. So now we have example 3.36, and it says 15 drivers are taking part in a car race. How many different ways can the top 6 positions be filled? So we have 6 positions. So let's imagine that we have these 6 positions. How many ways can the top 6 positions be filled? 15 different ways to fill in the first position, right? But then once somebody is chosen for that first position, there would be 14 left for the second position, and so forth. There would be 13, and then 12, and then 11, and then 10. So this would be 15 times 14 times 13 times 11 times 10, and this is a pretty large number. This is going to be 3,603,600 different ways. But this is doing it intuitively. We could do this in a different way. Notice that this is the same as saying 15 factorial, right? Divided by, and notice that we would say 9 factorial, right? Because that would leave us with this same multiplication from 15 to 10, because once we get to 9 factorial, the rest would cancel out. Now, this is the same as a permutation. And the permutation, which is symbolized as this, you would say 15 permutated into 6 spaces is going to equal 15 factorial divided by 15 minus 6 factorial. And notice that this is, again, 15 factorial over 9 factorial, and we would get the same answer. So this is a good example to introduce permutations. For permutations, we define them in terms of n and r. This would equal n factorial over n minus r factorial. So this gives us the number of permutations of n objects taken r at a time. Suppose they ask you for a 3-digit code, and the 3 digits must be different. So that means that we would have 3 positions to fill in. And because it's a code, it can start with 0, no problem, right? So we would have 10 digits that we could place in the first position, but then we would have 9 for the second position and 8 for the third position. But as we saw before, this is the same as saying 10 factorial divided by 7 factorial, which really is simply a permutation. Now let's look at a different case. Let's say they ask us to pick 3 numbers or 3 digits randomly. For example, let's say 1, 2, 3. But here the order doesn't matter. I could have also picked them in a different order. I could have said 1, 3, 2, or 2, 1, 3, 2, 3, 1, or 3, 1, 2, and 3, 2, 1. So notice that we have 6 different cases that we would have to discard from this here. In other words, we would have to divide this by 3 factorial. If we rearrange this, notice that it would be 10 factorial over 3 factorial times 7 factorial. But notice that this is the same as saying 10 factorial over 3 factorial times 10 minus 3 factorial. But this is simply the definition of a combination. So that means that the difference between a permutation and a combination is a fact of whether or not the order of the numbers matters. Now we continue with example 3.37, and it says, a lottery has 45 numbers. If you buy a ticket, then you choose 6 of these numbers. In how many ways can you select 6 numbers from 45? So this is a case of a combination. 45 positions in combination with 6 choices. So this is going to equal 45 factorial divided by 6 factorial times 45 minus 6 factorial. Now we're not going to do it by hand. I'll just plug it into the calculator, and it would give 8,145,060 different ways you can select 6 numbers from 45 options. Now we are in example 3.38, and it says, in some card games, a standard deck of 52 playing cards is used, and a hand is made up of 5 cards. How many possible hands are there? So notice that when we get a hand of cards, it doesn't really matter in which order we get them, correct? That means that this is a case of a combination. So since we have 52 different cards and we have to pick 5, it will be 52 in combination with 5. This is going to give us 2,598,960 different combinations. For part B, it says how many possible hands are there with 3 diamonds and 2 hearts. So cards can be in 4 different groups. They can either be hearts, they can be diamonds, they can be spades, or they can be clovers. So there's a total of 13 diamonds, 13 hearts, 13 clovers, and so forth. So this would also be a case of a combination because the order doesn't matter. So we would say, all right, so I have to pick 3 diamonds from 13. So we would say 13 and 3. This is one possible combination. And then we would have to multiply this by the other possible combination, which is out of 13, we pick 2. And then all we have to do is plug this into the calculator, and it's going to give us 22,308 different possible hands. So next we'll do example 3.39, which is the last one on this video. And it says a code is made up of 6 different digits. Very important word, different. How many possible codes are there? Now there's 2 things here. First, is the order important here? Let's say I have a combination that says 2, 5, 9, 0, 1, 6. Now I could rearrange these same numbers in a different way and it's going to be a different code. Therefore, this is the case of a permutation. In a combination, order doesn't matter, but in permutations, order does. So notice that they say different digits. That's also important. This is also something that we have to take into account to consider if a situation requires a permutation or not, because if they had said just 6 digits, then the solution would simply be 10 to the 6, right? 10 times 10 times 10, 6 times, because we could repeat numbers and so forth. But the digits must be different. Therefore, this is a typical case of a permutation. Now notice that we could also do this manually if we said, well, I would have 10 different digits that are possible for the first position, and then 9, and then 8, and then 7, and then 6, and then 5, and then multiply this and I would get the same answer. But this is the same as a permutation, like I said. So we would have 10 digits to choose from for 6 positions, and this is going to equal 151,200 different codes.